shown, and they would like to talk now. Do you want the lights on?
Yeah, I think it's better to see some of the images. Okay. Well, welcome back, guys, and thanks for having the fortitude to make it through the fourth lecture. So this lecture will be mainly about the devices and how we might get ultimately to higher efficiencies, above the 7 or 8%. And so the first topic I want to mention is the voltage, the open circuit voltage, the VOC. So we've seen this diagram before. This is an illustration of the band offset between the donor material, the P382, and the acceptor material, the PCBM. And we said we have this very large band offset over 1 eV, which is a big source of energy loss in the system. So the question is, can we vary that energy loss a little bit? So this actually refers now back to, again, the talk of Ricardo, the previous speaker, in that we can use some inorganic materials like zinc oxide to investigate the effect of band offset. So in particular, if you take zinc oxide and you mix a little bit of magnesium into the zinc oxide, and you substitutionally dope the magnesium, you can change the band gap. You can change it by quite a bit. So if you put in magnesium, something up to like 40%, you can change the band gap from 3.2 electron volts up to 4 electron volts. So a really big change. And what you're doing when you do this is shifting the conduction band of the zinc oxide, or essentially the LUMO in terms of organic materials. You're shifting that closer to vacuum. And that's reducing this band offset, which is this energy here. Now this diagram, I've reversed it from the previous diagram. I have the electrons going to the left. The previous diagram, electrons are going to the right. But it's the same idea. So we're going to reduce this band offset and increase the effective band gap between the donor and the acceptor. Therefore, we would expect a little higher efficiency. So the first question is, when we put in the magnesium, do we really still have zinc oxide material? And if we look at some X-ray diffraction of the system, if we look at pure zinc oxide, and Ricardo had showed a very similar plot, here are peaks associated with the different lattice planes of zinc oxide, 100, 002, 101, here's a 110 plane. If we put in magnesium, we put in 10%, 15%, 20%, we're not disturbing those peaks very much. Get up to 40, 45%, then you get some new peaks growing in, and now we're starting to see a really different material. And that material is going to be insulating. So too much magnesium in the system, you get magnesium oxide, which is an insulator, not a semiconductor. So nonetheless, we can look at the optical band gap of the system, and as we increase the magnesium content, we're pushing the band gap to higher energies. Okay, so what is the effect on the device? So as we expected, as we put in magnesium, we get a larger effective band gap. And sure enough, the open circuit voltage, this crossing point here, shifts to higher and higher values. So we can just summarize that. If you look at the black curve, which is open circuit voltage, we start at about 0.5. And as we add magnesium, we get up to close to 0.9 volts. So we're really increasing the effective band gap of the system. So the question is, what happens to the current? So we said that as we decrease now the band offset, there's less of a driving force for the electron transfer. So we might expect that the current to go down. Luckily, we didn't see that. So the red is the current. We started at, well, this pretty low value of 0.3 milliamps per centimeter squared. As we add magnesium, decrease the band offset, that current actually goes up a little bit. At least to a point. When we get too much magnesium, we get the insulating behavior and the current will crash down. But at least for the low values of magnesium, we get both the better voltage and the better current. So this is good news. This means that we could presumably lower the band offset between the materials, get a higher voltage, and not lose current. In this case, we actually gain a little bit of current. So this band offset issue is important, and we're continuing to study it. The question is that the whole story? Are there more factors that control the voltage? Of course, the answer is yes. So in our original picture, the open circuit voltage, the VOC, is the difference between the HOMO of the donor and the LUMO of the acceptor. That's the effective band gap. Okay. There are some other terms that come into play, and these have to do with the recombination processes in the material. So we said that as you drive photons in the system, you split the quasi-Fermi levels. Well, if there's recombination, those quasi-Fermi levels will come back together. right? And that'll reduce the voltage. So recombination will reduce the voltage, that's a bad thing. So Jan Anton Koester, who's now at the University of Groningen in the Netherlands, has studied this and has derived a relationship for how the recombination affects the open circuit voltage. So there's a thermal term here, kT over Q, and then we have the log of 1 minus P, where P is the probability for the exciton to dissociate. That's the probability that you get charges. And then gamma. So gamma is the recombination rate constant. In particular, it's the Langevin recombination constant. And we're going to talk about this Langevin stuff a little bit more. But this is saying how fast the charges are recombining and how quickly those quasi-Fermi levels are coming together. And then there's a term for the density of states. And then G is the generation rate, how fast the excitons are coming in. So anyhow, you could use that equation and, for instance, plot out open circuit voltage versus the conduction band density in sub C, and see that as you turn up the conduction band density, the voltage comes down. Now this agrees with our description that the quasi-Fermi levels control the voltage. If the density of states is larger for a given number of charges, the splitting of the quasi-Fermi levels has to get lower. There's more available states. So if we plot out, for instance, here is energy, here is density of states, G of E, the more states available, the more charges we would need to fill them to get a higher voltage. So here's an example. We put in this amount of charge, the blue amount of charge, and that's how much voltage we get out, right? So if there's more density of states, same amount of charge, the voltage would have to get smaller. And that's what you see. That's what you see here. So to tie this with the previous part of the lecture, we could also think about if we have defects in the material. So the way I've drawn it, here's the HOMO band, and you see it has a nice Gaussian shape. Here's the LUMO band, that's nice and Gaussian. But what if there's some defects? What if there's some density of states in the middle of the gap? What's that going to do? Well, first of all, there'll be charges stuck in that position. That'll consume some of the charge density. But also, this energy can pin the Fermi level. That is, the chemical potential can be stuck at that level. So the net result is a decrease in voltage. So not only is recombination bad, but these defects are very bad for voltage. And we want to prevent both in the device. So this is one of the main equations we have for VOC right now, but it's not even the whole story. There's even more subtle effects. And I'm going to talk about one more of those. So this study will be based on a series of different fullerenes. So far we've looked at the fullerene PCBM, where we have a C60, there's a phenyl group here, and a side chain here, and that's the structure. Well, my chemist colleague at University of Groningen, Kees Hummelen, who's one of the real experts in fullerene synthesis, has made a series where he's extended this molecule, this is now a fluorine molecule, and put on some alkyl side chains. And these alkyl side chains can be 6 carbons long, 8 carbons long, 10 carbons long. So we've got this series of molecules, and we're going to call these, instead of PCBM, we'll call them FCBM, F for the fluorine that's here. Now, the language is kind of complicated here. You've got a fluorine side group on a fullerene molecule. So it's a fluorinated fullerene, which is kind of tough to say. Now, if we measure the LUMO level of these molecules, they're actually all pretty close, all within about 20 millielectron volts. So based on our simple band offset figure, we should get the same voltage from all these molecules. Well, guess what? We probably don't, otherwise I wouldn't be talking about it. It turns out we get a little extra VOC from these new acceptors, from the FCBMs. So here's just the table. This isn't the greatest way to present the information, but if we take P3HT PCBM and just kind of make a device very, very quickly, we get 575 millivolts. It's not the best device we've made, but it's just an example. Now we put in, instead of the PCBM, we put in the FCBM, the fluorinated one, that has 6 carbons in the chain. Somehow we get an extra 30 millivolts of voltage. Put in the F8, now there's 8 carbons in the chain, we get another 15 millivolts of voltage up to 620. And then you put in the F10 and it comes down a little bit. But somehow between F8 and PCBM, we get about 45 or 50 extra millivolts, even though the LUMO levels are the same. So our simple description is not quite right. And I should say for other materials, this difference, or the extra VOC, can be a lot more. It can be over 100 millivolts. So what's going on? Well, one thing that's happening is as you increase the length of the side chain, let me go back here. So you increase the length of the side chain, you're limiting the interaction between the donor and acceptor, physically pushing them further apart. So this has consequences for the current in the device. And in particular, what it can do is reduce the current in the dark. So when we have a diode, we have our standard diode equation. We say that the current in the diode goes as Js naught. This is some, it's called the saturation current, and then a function of the band gap, exponent minus Eg over Kt. This is from standard diode equation, the Schottky diode equation that you would see in an inorganic device. So this Js naught is the saturation current, and when you decrease the interaction between donor and acceptor, it is hypothesized that Js naught also decreases. So we're decreasing the dark current in the device. And when Js naught is smaller, Js is smaller. Js is smaller. If we look at the equation for the voltage, sorry, I'll do with this one. The Js is on the bottom. So smaller Js means a larger voltage. And this has been hypothesized by Van der Waal et al. In a paper in Nature Materials. So we think this is probably the explanation. Put on more side chains, more separation. We reduce this saturation current and get a higher voltage. Just to show a little better enhancement, we can now try mixing that FCBM with a different polymer material, different donor. So this is PCDTBT. This is this polymer here. And this has a little lower band gap than P3HT. And the band offset is a little bit, or the effective band gap is a little larger, so we get a little higher voltage anyway. But if we compare the FCBM with the PCBM, for the FCBM we get 930 millivolts, for the PCBM we get 850 millivolts, so we get an extra 80 millivolts, even a bigger increase than we saw before with the P3HT. So it's not specific to a given polymer, it happens for a whole variety of polymers, the very general phenomenon. So anyhow, there's more to the story that I don't have time for now. There's that issue of the charge transfer exciton that I talked about yesterday. That also influences the voltage. And this is a very hot topic right now in the field because that voltage drop is one of the biggest losses in the efficiency. So if we can understand that, we can get the efficiency up higher. Now you might ask, well, you're putting in a different acceptor material. How is it changing the morphology? How is it changing the charge transport properties? And we've just begun to look at that with a bit of TEM work. So these images also came from King Abdullah University through our collaborators. And the question was, if we put in these FCBMs, do they disturb those nice nanofibers that we started with? And the answer is they do, actually. So it's a little hard to see in this image, but there's very little evidence of those nanofibers here. So this is P3HC with the FCBM, the F6 CBM. And it was processed in the same way as PCBM would have been to create the nanofibers, but in this case, they're gone. And we can see in the sulfur map, so this is again a picture of where all the polymer should be, a little more uniform distribution than in the case of the PCBM. So this is saying perhaps we don't have those nice clean domains of polymer nanofiber and then amorphous or amorphous domain of the acceptor, that maybe the mixing is again a little more intimate.
What's the scale bar?
I'm sorry, this is 0.2 microns here is the scale bar. So this is about 2.5 microns on a side. Yeah. So apparently this FCBM with the longer side chains, it is disturbing the ordering of the polymer. Same for the F8. If you look carefully, there's some hint of the nanofibers here, but they're generally disturbed. And the same thing for the, well, that should be F10. This should be F10, yeah. So they all disturb the nanofibers. That means the charge transport isn't as good. And if you notice on the data I showed, the currents were a little bit lower. So even though we get higher voltage from these materials, we get lower currents. So maybe we can go and improve the situation with different processing, but for now, these don't give better efficiencies, but they told us about the physics a little bit.
I have a question.
Yeah.
So what are these sanctions that we are looking at?
So you're looking on the right?
Yeah, I mean, if you were to have the device, right?
Yeah.
Is this in the plane of the device?
This is looking perpendicular into the device. So this is a 2D projection of everything that you see. So in that sense, it's not ideal.
Because it could be that your fibers are actually running that way, and the resolution is not good enough to see.
That's right. You would not see vertically aligned fibers.
Right. That might be actually more ideal to have it in this way.
Would be, yeah. Now the fibers that we saw before were very long though. They were in the micron range, and the film thickness is 200 nanometers. So they certainly can't have that same length. But ideally, yes, we would have the sort of pathways. So now other groups are doing three-dimensional tomography where you can see the structure and you can rotate it with the nice pictures. My collaborators right now don't quite have that capability. Hopefully CU Boulder will have that capability. Yeah. Okay, so I want to go on to more device physics-y stuff for the electrical engineers in the audience. And so in the beginning we showed this picture where you have Fermi level alignment of the electrodes and you have these very straight bands, meaning a uniform electric field in the device. And now we'll talk about a refinement on that. And the refinement is, of course, those bands are not straight. The simple model is not correct, but the bands probably look more like that. They're more bent. And why that should be the case? Well, if there are any carriers in the material, some dark carriers or dopants, that's going to disturb the field distribution. Now, I already said that there's a good evidence that there are defects in the material coming from the charge transport. And those defects are likely to have to impart some dark carriers or dopants in the material, and therefore give you something like this. So we can measure those directly using impedance spectroscopy. And some of the early measurements that were done were by a colleague at NREL, Anthony Morfa, he's now in Melbourne, and Yao van der Lagemat, who's still at NREL. And they came up with a number of about 10 to the 16 per cubic centimeter of carriers. So if you're familiar with semiconductor physics, that's a fairly low number in terms of how high you might dope silicon. You might dope silicon 10 to 18 or 10 to 19. But it's high enough to bend the bands, to have significant effect on the bands. Okay, so a little sidetrack into impedance analysis for the specialists in the audience. How do we actually extract out those carrier densities from impedance? So we can take our device, and the first thing we want to do is fit an equivalent circuit to the device using a capacitive model. And for that, we'll make a Nyquist plot. That is, plot the negative imaginary component of the impedance with the positive real component of impedance. And in this case, the red curve is what we measure, right? We take the device, here's the device structure, just measure the impedance and then plot out the imaginary versus real part. And the green is a fit to an equivalent circuit. In this case, the equivalent circuit has two capacitors, 1 and 2. We see the fit is not very good, so we decided to go to 3, and my graduate student, Shaheen decided that this was a nice circuit. So there's 3 capacitors, there's 2 in series here, and there's 1 in parallel with it on the other side. And that actually fit the data very, very well. Now, he didn't pick that at random. This circuit is based on his guess at what the device physics might be. And in particular, the C1 capacitor is the geometric capacitance of the device. Right? You've got an active layer, 2 electrodes. The thing is basically a capacitor. All these devices are basically capacitors. Right? So there's the geometric capacitance. Now, what are C2 and C3? Those are coming from the interface. So the interface, there's a bit of charge transfer, there's some depletion, and that gives you an extra capacitance, C2 and C3 at each interface. So we can now attribute a physical description to those capacitances. One is geometrical. C2, we're going to say, is the P-dot interface. That's the positive collecting interface here. C3, in this case, is the calcium interface, is the negative interface there. Now, how do we come to this assignment of interfaces? Well, we looked at the values for the capacitances and the values for the depletions and various other information. We decided that was the case. Okay, so that tells us something about the equivalent circuit, but how do we get the number of carriers out of the technique? And this is very standard stuff. If you look in Physics of Semiconductor Devices, the Bible of Semiconductors by Z, then you'll get all the story about what's called Schottky Analysis. So what we assume is we have a Schottky barrier at the interface, right? So you've got, here's a metal, oops, sorry. You've got a metal, here is the semiconductor with a Fermi level that is, this is p-doped, and you put them in alignment, you have to have Fermi level alignments, and this means there's some band bending in the semiconductor. So there are standard equations you could fit. So 1 over c squared goes as 1 over the carrier density. So if you plot 1 over c squared, and there's a bias voltage in here, what you do is apply a voltage to the device. Ideally, this will give you a straight line, 1 over c squared versus the bias, and the slope of that line tells you the carrier density. It should be n sub a, the carrier density. And whether or not it's positive or negative tells you that you're either at a positive electrode or a negative electrode. Okay. Okay, so we can do that in these devices, kind of. It turns out that if you use a normal device where the active layer is about 200 nanometers thick, if you make a plot of 1 over c squared versus voltage, it doesn't look like what the Bible says it is, but it's a little bit distorted. So what you have is sort of a turn on, but then there's a kink in the data. And oftentimes, this is actually one of the prettier ones. The ugly ones, the kink just goes straight, and the data sort of dies. So what you need to do is make a much thicker device. So if you go to something like a 5-micron device, now we can capture our classic behavior, a nice straight line here. We can fit a slope and extract our carrier density. So what's happening here, we actually are not fully sure, but we think that for a very thin device that the depletion is already a significant fraction of the device. The depletion is about 100 nanometers, is about half of the device, so the model just breaks down. And when you turn up the voltage, you increase the depletion width, and the depletion width gets to about the dimension of the device, and the model breaks down. So a very thin device, then we can really push the depletion through the thickness of the device. Okay, so what therefore is the result? So what we come up with, if we fit now to our two capacitors, the C2, which is the positive interface capacitor, and the C3, we get equivalently a pretty low carrier density for the positive electrode. We get about 10 to the 14. For the negative electrode, we get close to 10 to the 16. So this tells us that there's very little depletion actually at the p-dot interface, and all the depletion is essentially at the metal interface. Right? So our band picture will look like band bending towards the negative electrode. So do we have any other evidence for that? And the question is, the answer is yes, we do. So we talked about time of flight mobility measurements, where you take a material, you illuminate it, create charges on one side, and then follow the transit of the devices, of the charges across the device. So normally that would give you this straight line where you're seeing the constant velocity of the carriers, and then a decrease as the carrier is exiting the device. Well, if you look at very low voltages, you do not see that, but instead you see this sort of double dip. So the carriers come down, go back up, and come down again. So at first we looked at that, we did not have a good explanation, but my colleague Yao van der Lagemat said, aha, this is an indication for band bending in the device. And if we assume that the band structure looks something like this, where here's our Fermi level alignment, here's our two electrodes, and under the simple picture we would assume straight lines here, right? But if it's not the case, then what we have is a flat region, and then all the band bending towards the negative electrode. So all the field is here, this is a field-free regime, this is the field. So the only way the carriers will move in this case is through diffusion, just chemical diffusion. Create a bunch of carriers here, there's a carrier density gradient that will diffuse in that direction. So that's what you see in the early times. This is just a diffusional transport. Then the carriers hit the electric field region and they get accelerated towards the electrode, and that's what you see here. There's an acceleration of the charges, and then finally the charges leave and they go down. So that was the hypothesis, and then Yao said, well, I should be able to calculate some quantities here. In particular, we have an equation for the depletion width as a function of electric field. So, and we know the total width, so we can tell how much space the carriers have to diffuse and how much they have to drift in the accelerated field. So we can probably fit some equations to that. This is just showing that at high electric field that you don't see that behavior, because at high electric field you push the depletion all the way through the device and you again get the straight bands. Okay, so we can fit that to some equations. So the depletion width is given as a standard equation out of the physics semiconductor book, out of the Bible. Just the depletion width goes to the square root of essentially the applied field. So if we put that width into an equation that describes the time of transit, what we can say is the transit time has a diffusional component where the distance d is the width of the device, 1 over alpha is the absorption depth, and now here is the depletion width. So we can say that essentially the total distance traveled is the total thickness minus the depletion width over 4 times d, the diffusion coefficient. We can fit a transit time. So it turns out that that model, that simple model, fits the data very well. So here's the transit time, tau sub d. Here's the applied bias, that would be the v. And here is the data for a number of different pulse powers. That is a number of different initial charge densities. And on a log linear plot, this is essentially straight for a while and then it takes off near the end, but it fits the data very well. So this is more evidence that we don't have uniform fields in the device, but you've got band bending towards one of the electrodes. So out of this system, we can actually extract a lot of physics. Not just the field distribution, not just depletion widths, but something about the carrier dynamics and the recombination. So just to complete the story here, that you can also, of course, measure the mobility versus the field. That's the whole point of the time of flight. And in this case, we get something that looks relatively straight according to, again, our exponent of the root of the electric field, but not perfectly straight, but a little bit of positive bend. Pretty similar to our model before. And now to this, the dynamics. What do we get out of the dynamics? So what we can do is, as we're measuring the carriers coming out of the device, we can integrate the total charge coming out of the device as a function of time. Right? So as the carrier is coming out, you just count up all the charges, and you do that for a variety of pulse powers. And what you find is that these have different slopes. Well, why do they have different slopes? That's because the recombination of charges is different at different pulse powers. Right? So for very high pulse powers, at 16% of the pulse power, there's more carriers around, recombination is more likely, this slope is steeper. Very low pulse powers, carriers are separated further apart, lower recombination rate, the slope is shallower. So we can look at those slopes and get a measure for the recombination rate, and that's what Anthony Morpher had done. So here is the recombination rate. This is in units of 10 to the third per second. Right, so this would be 30,000 recombination events per second, for instance. And then this is percent transmission, or a measure of the carrier density in the film. So we talked about Langevin recombination, which is a standard formula for recombination. And the conventional formula is that the recombination rate R should go as gamma, where gamma is the recombination constant, times n times p. N times p are the density of electrons and holes, minus ni times pi. Now ni and pi are the intrinsic carriers in the film that would be thermally, for instance, thermally generated. These are very small. This would be like 10 to the 10, 10 to the 11 charges per cubic centimeter. So you can basically ignore this term and just say the recombination goes as the constant times n times p. More charges means higher rate. Now the constant is the Langevin constant, should go as the mobilities of the material. So we alluded to before, as you turn up the mobility, the charges have a higher probability of colliding. It's the reverse of the Onsager process. The recombination rate should be higher. So higher mobility is actually a bad thing for recombination. So what we can do is define now a rate constant for essentially what's called monomolecular recombination. We assume Ni and Pi are 0, and we assume that the population of N is much higher than the population of P, and therefore the rate constant is just the sum of mobilities times the P. This is a monomolecular recombination rate. So this is what the theory tells us. If we calculate those values, we get something like 2 times 10 to the 6. So it should be 2 million recombination events per second. But the data is much lower than that. It's 2 times 10 to the 4th. It's about 100 times smaller than that. So what we measure experimentally is that the recombination rate is much lower than what standard theory would suggest. And we're not the only ones to measure this. There are 3 or 4 other groups, maybe 6 other groups, who have come up with the same sort of relationship. So in the working device, the recombination is much slower than we would expect from conventional theory. This is a good thing. This means the device can work well. If this was the recombination rate, we'd have big trouble. The OPV device wouldn't work very well. So why is it the case? Why is this so much lower than this? Well, we're not really sure, but it probably has to do with the fact that we have 2 different materials in the system. We have electron donor, electron acceptor, and they're spatially separated to some extent, right? They have different morphologies, and so the electron in the donating phase doesn't have complete access to the hole in the accepting phase. Actually, reverse that. Electron in the accepting phase and hole in the donating phase. They don't have complete access, so the original Onsanger formalism, where you have hopping in a uniform, random hopping of Brownian motion, is not satisfied here. These guys have some constraints as to where they can hop. So the bottom line is that the experimental value is a lot lower. So that's a good thing. And again, this is a hot topic. A lot of people are studying this at a fundamental level to try to understand why that really is that value. Okay, so we can put all these things together. We talked about the voltage, I talked about the current, talked about the band gap. And what we're doing at NREL is making sort of a universal model that puts all these inputs in and tells you what the device behavior should be. And this model is being written by a senior computer scientist, Peter Graff. He's in the Scientific Computing Center. And we're basically borrowing a lot of material from this paper by, again, Jan Anton Koester. And Jan Anton is also working with us to try to improve things. But this is just using standard semiconductor physics equations. We saw some of these the last couple days. You've got the Poisson equation, continuity equations, drift and diffusion equations, generation equations. So nothing special here. The only thing that we are doing is adding an extra term. So you've got the electron density, the hole density, and we're adding an extra term here, which are the dark carriers. These are the defects in the material. So that's what we want to study. We added these defects in the carrier. Otherwise, we're making a one-dimensional model. We're solving these equations numerically, and we have a bunch of inputs that we can optimize for the device. Okay. So just a few details about the model. What we assume is this kinetic scheme that was developed by Koester. And the idea is that we've got the donor molecule, the photon comes in, that gives an excited state donor, E star. And from this we create that partial charge separated state, that charge transfer exciton. That sits here. And this acts as a reservoir for free carriers. So here the electron and hole are not completely free, but they're separated a little bit. And then they have a certain rate constant, K dissociation, for being fully separated. So that's one of the kinetic pathways. Those free carriers can then recombine through the Langevin process, come back together. So there's another rate process here. And also there can be direct recombination, so those partially separated charges can just come together and go to the ground state. So this is a kinetic scheme. We can come up with rate constants for all those values and stick that into all of those equations for device physics and come up with what's going on in the device. So one thing we can look at are, for instance, we can look at the device, and these numbers are really tiny, but I'll just tell you, here is the x dimension of the device, and here are the current densities. So we can look at the current densities in the device, and under, for instance, short circuit conditions. Sorry.
What was x, did you say?
So x is the spatial position in the device. In this case, 120 nanometers. Yep. And so this is looking into the device. Here is the carrier density. So this is under short circuit conditions, meaning the electrodes are perfectly lined up. And what you see is that the carrier densities are relatively flat. In this case, the green are the the red are the short circuit current densities, and the green are the open circuit current densities. But anyhow, we can get a picture of what's going on in the device. On this side is the potential, that is the electric, what it would be the electric field. And so under short circuit, this is where we have the high built-in field in the device, and it should be a perfectly straight line. And it generally is. You see a little bit of bending on the edges, a little bit of that depletion in the device. If we then go to open circuit, where we allow the electrodes to develop at some voltage, then we have more or less a field-free regime in the device. Okay, so we're going to see more examples of that. First of all, what can we do with the model? Well, we can fit the
Excuse me,
JD.
Sean, why do you have depletion at 0?
So even if, so in this fit, there are no dark carriers. So this is a completely intrinsic material. It's a perfect material. But if you solve the Poisson equations at the electrode, you get a little bit of band bending here anyway. You get a bit of depletion naturally, because you fix a certain carrier density at the interface condition. So the interface condition is 10 to the 17, 10 to the 18 carriers right here. That's the metal electrode. And so you naturally get a little bit of band bending here, even if it's a perfect material. Yeah, and that follows out of the Poisson equation. Yeah. So, okay, so we can model the JV curves. So here is a fit to this PCB TBT material. This is data that was made at NREL. This was a device that was close to 7% efficiency. And we have a whole host of input parameters that we put into the model. There's like 11 different parameters. There's the generation rate, how fast the photons are coming in. There are the density of states for electrons and holes. That's N sub C and N sub V. There are the number of dopants in the material, N sub A, N sub D. The recombination rate, K sub F. The hole mobility, electron mobility, all these inputs here. And we can make educated guesses at these based on experiments and other characterization. We do the best we can. And in the end, you can get a pretty good fit. Now, it's not too surprising with 11 parameters that we can get to fit. But we try to make sure that these values come from some other experiment to the best we can. Yeah. So I should say that our plan is to finish this model and to put it, I'm going to put it on my homepage and make it publicly available. So for you guys who do devices, hopefully we'll be able to get this into your hands to be able to play with. But we still need to convince ourselves that it's really working properly. Okay, back to the issue of the defects. So remember in the model we had that extra term, the C of X, the dark carriers. So let's start turning up the dark carriers and see what happens. Well, if we put in 10 to the 15, which is again a pretty low number, so the red curve here is, the green curve is with no dark carriers, and the red is with 10 to the 15. There's hardly a change. Go up to the 10 to 16, and it looks like we lost a little bit of short circuit current, and the fill factor now is not as good. Go to 10 to the 17, now we really lost a lot of current, and fill factor is really very poor. So what's happening here, well, as you put in dark carriers, you are screening the electric field so that band bending is not as much in the bulk of the material. And with lower electric field, the carriers are not escaping as much, and you're getting more recombination, lower current. So those dark carriers coming from the defects, not surprisingly, are a bad thing for the operation of the device. And we have some data from a number of different collaborators that agree with us that the dark carriers reduce the current. You might notice that the voltage goes up a little bit as well, and we've got some explanations for that. Okay, so now we can go and use the model to see what's going on with the bands inside the device. So again, if we have Na equals 0, no dark carriers, then under short circuit conditions, we see the mostly straight band with a little bit of bending here and here. Here are the carrier densities. We go to 10 to the 16, you start to see a little extra bending here, a little flattening out here. And now if you go to the 10 to the, or 5 times 10 to the 16, sorry, 10 to the 17, now you've got lots of bending here and a real flattening, and a real flattening here. So, yeah, sorry, I reversed the electrodes again. Here's the negative electrode, here's the positive electrode, and you see most of the bending at the negative side. So this seems to fit now with our time of flight data, and it seems to agree with the impedance data and the modeling data all agree that we have big band bending right at the negative electrodes. Okay, so I just want to wrap up the whole series of 4 lectures with final discussion about the efficiencies and how we can maybe get them a little bit higher. So we're starting to get a handle on the device physics. There's still a lot more to go, but where ultimately can we go with the efficiencies? Of course, a lot of people have looked at this. There's a number of publications over the last 7 to 8 years, and a common figure that you would see is that an achievable efficiency from these devices is about 10 to 11%. The exception is a paper that's coming from Moritz Rieda at the Dresden group saying you can get 15%. So let me walk you through this number of how you might get to 11% using these device architectures. Okay. So first of all, we do need to optimize the band gap, and we said the optimal is around 1.4 eV. That's 880 nanometers. So it'd be nice to have material right there. We do have materials that are right there, but they're not ideal in terms of charge transport and recombination. But let's assume we can fix those problems. Then if we were able to harness all of those carriers, so 1.4 eV gives you about 33 milliamps per centimeter squared. But let's take a realistic number and say we can get 60% of those. And this number is not arbitrary, but in the P3HT device, we get about 60%. So let's use the same ratio here. 60% times 33 would give us 20 milliamps per centimeter squared. Should be an achievable number for a current. In terms of voltage, so if we can minimize the band offset, get a higher voltage, so let's assume a band offset of 0.3. Right? This is really optimizing it because right now we're over 1, but let's bring it down to 0.3. And we said we always lose a little bit of voltage due to recombination, and typically you lose another 0.3. So under these conditions, we would get an open circuit voltage of 0.8. And that's a very achievable value. We have lots of devices that can do that. And then if we make a good diode, we can get a very sharp turn on, a fill factor of 0.7. That's also been achieved. So what do? We just multiply these three numbers together, 20 times 0.8 times 0.7, divide by the incident light intensity of one sun, which is 100, and voila, 11.2% efficiency. See, wasn't that easy? We got 11%. So all of the companies that are working on this and a lot of scientific groups believe that we can do this, there are no obstacles to this, and that's the immediate goal for single junction devices is 11%. Right now we're at 8.5 or maybe 9. So we've got a little bit more to go. Now the question is, how do we go much higher? 11% is really on the low end of what could be commercially viable for making large-scale arrays out in the field. So silicon devices are 22%, CAD telluride are 15%. So to really be competitive, organic PV needs to push to those higher values. So we've got a pretty clear pathway to 11%. But what if we want to get to the 15 or even higher? So, of course, there are lots of different mechanisms for doing that. One is a tandem device, the multijunction device, which has been mentioned a couple times, and there's lots of work on that in OPV. The other side of the equation are some more exotic mechanisms. So instead of being limited at 31%, can we use multiple excitons? Can we use hot carriers? Singlet fusion, upconversion, all these exotic strategies, right? So if you look at some of the original work by Martin Green in Australia, he categorizes photovoltaics into three major categories. There's first generation, which are basically silicon devices, and if you plot them on a cost per meter squared basis versus efficiency, they cost a lot, $200 to $400 or $500 per meter squared. Efficiency is about 20%. So the second generation would be thin film materials like copper, indium, gallium diselenide, or CAD telluride. They cost a lot less, below $100 per meter squared, but efficiencies tend to be a little lower as well. So the question is, how can we get into the third generation of PV that is very low cost and very high efficiency? So all these mechanisms are potentially a way to get there and to exceed the Schottky Quasar limit, which is right at about 31%. Okay, so first about tandem devices, and there's really a lot of work going on in that area. So I said Heliotech has efficiencies over 8%, and their devices are in fact tandem devices. So they are thermally depositing multiple layers and creating multiple junctions, and that's a double junction device is their 8% device. You can also do this with polymer devices. There's a couple groups doing this. One is René Jansson's group in Eindhoven, and he has actually demonstrated that you can build up multi-layer stacks using zinc oxide as one of the buffer layers, and can create up to 6 or even 7 junctions on top of each other, just adding up the devices. And in this case, you add the voltages, and you can get total voltages of 3 or 4 volts, 5 volts out of these devices. and that works pretty well. The currents are not great, but the voltages do add. Here's an example coming from that same paper. So here's a single junction device, about 0.6 volts, and now here's a triple junction device, it's over 2 volts. So you see an increase in the voltage. Of course, ideally you want to retain the current, but we haven't done so in this case. So there's a recent review on this topic by the group of Christoph Brabetz, where he goes through all the different devices and attempts at creating multi-junction devices. So again, this is hard to see, but here's thermally evaporated devices. These are small molecule devices that are using nanoparticles as a recombination layer or interface layer. And here's a polymer device where you're using either zinc oxide or some other oxide as an interface layer. So I'll breeze through this, I'll let you look at that on your own. And even more recently, the UCSB group has also made multi-junction devices from polymers using this low band gap material, the PCP-DTBT we looked at briefly before, and making a double junction of here's the high band gap component, the low band gap component, put them together, put an interface layer of TiO2 in there. Now you can add the voltages and get over 1 volt there. So I'm just showing you a lot of groups are trying this, and we're interested in NREL at doing this as well, and it's possible. Okay, so finally I want to touch upon those more exotic mechanisms. And I think multiple excitons have been mentioned a little bit this week, and I just want to briefly highlight them in terms of what they can do. So what is the advantage of the multiple exciton? Well, if you have a conventional exciton, and let's say you have perfect quantum efficiency, as you increase the photon energy, the quantum efficiency stays at 100%. Right? You get 1 electron per exciton. So with multiple excitons, ideally for every multiple of the band gap, and this is assuming a 1 eV band gap system. So when you go to twice the band gap, now you suddenly get 2 electrons. 3 times the band gap, you get 3 electrons. Right? This would be the ideal staircase for MEG. So if you calculate what's the theoretical efficiency versus band gap, if you just have the single exciton, then we get back the original curve we saw before, with an efficiency of 31%, band gap of 1.4. If now you assume a perfect staircase, now the optimal efficiency has gone up to 40%. Band gap has come down a little bit as well, but about 40%. You can get even higher values if you have concentrated light. You can get this up to 50%. And if you use multiple excitons in a multi-junction tandem device, then you can get this even higher, above 50%. So, very promising approach. There is some debate over the validity of multiple excitons. Do they really exist? Do they really work? But I just point out that there's a recent result from Bruce Parkinson's group at the University of Wyoming. This was published in October in Science. What he did was take a single crystal material of TiO2, single crystalline TiO2, and attach to it some lead sulfide quantum dots. So the lead sulfide has a low band gap, I think it's around 0.8 eV, and spectroscopically has been shown to exhibit multiple excitons. This has been shown at NREL, this has been shown at Los Alamos, a couple places. But no one has been able to extract any charges out of those quantum dots, at least above 100% quantum efficiency. So Bruce's group is claiming they have done it. So what they've done is taken a monolayer or sub-monolayer of quantum dots, attached them to TiO2 through a carboxylic acid group. And so you have the sub-monolayer group, hit it with light and measure the number of charges that come off. So what they plot are the absorbed photons per converted electron. Every absorbed photon, how many electrons come out. And you see for photon energies, something like 3 times the band gap or higher, they're demonstrating above 100% quantum efficiency. So there must be more than 1 exciton in the system, and you must be harnessing more than 1 electron per photon. And in the best case scenario, there is something like 4 times the band gap, they're getting almost 200% quantum efficiency. So this is a big deal. This is the first real evidence that you can maybe harness these multiple excitons. It is not without controversy. It's pretty hard to measure accurately the absorption of a sub-monolayer film of quantum dots and to include all the optical effects and optical field effects. So I think that probably more analysis needs to be done, but it's encouraging sign. Okay, so I just want to wrap up with something a little more inspirational, which is that we have all these synthetic systems, and I've showed you, of course, a tiny slice of all the potential architectures for devices. But what is one thing we can use for inspiration is Mother Nature. And what can we learn from Mother Nature? Well, first of all, the structures in Mother Nature and natural photosynthesis are way more complicated than our materials. We make polymers that are very homogeneous. There's a monomeric unit. We repeat it 1,000 times, and that's our material. But of course, the natural light harvesting complex is much more sophisticated. And it was first resolved by the Isaac group at University of Glasgow. And I'm sure you've seen pictures like this of nicely ordered structures. You get this helical structure, and embedded in it are different chlorophyll molecules. There's another three-dimensional picture. So first of all, the Mother Nature is much more complicated structures. And these structures are not arbitrary. The orientation and position of the chlorophylls has been optimized through evolution to yield the best migration of energy in the system. And there's a lot of people looking at that energy migration. And one of the leading groups is Graham Fleming at the University of California, Berkeley. And what his group has found is that quantum mechanics is playing a role in natural photosynthesis, right? So there are coherent phenomena that are moving the excitons around. Create an exciton in one chlorophyll that can be transferred to another chlorophyll in a coherent fashion, which is pretty amazing because the plants are existing outside at room temperature, biological temperatures, yet still coherence is able to be seen. So how do they know that? Well, just looking at the spectroscopy, they can isolate these light harvesting complexes and look at, for instance, photoluminescence signals as a function of time, and you see quantum coherence, you see beating, right? Something like Rabi oscillations. So that's the evidence that there's coherent processes going on. And the theorists have looked at this in detail, and indeed it's possible to have coherent processes. So Mother Nature is using quantum mechanics in a very sophisticated way. We are not doing that in our devices. So our devices, we're just basically throwing this stuff in there, trying to make things a little bit ordered, but we have no idea about quantum coherence. So let me suggest to you that that's a way we can go in the future. There's a number of people who have some ideas about this, but we don't have any working devices that can show the quantum coherence. So I think an exciting avenue for the future. So that's the last thing I had to say. Well, thank you for sticking around for all 4 lectures. And I'm happy to take questions now or throughout the day. So thank you very much.